Thanks, Natasha. Okay, so I think my introduction of the university will be pretty short. So, but feel free to ask questions now or on Sunday when we talk with you. So, as you know, we are from the Faculty of Informatics of the University of Lugano. The Faculty of Informatics is a pretty new faculty at the University of Lugano, who is also a pretty new university. So, the university is about 14, 15 years old now, and the faculty has been there for about 5 years. We have a bachelor program, a master program, and PhD program. I don't think you care about bachelor. I'm sure you all have more than that, probably. The master program that we have started 3 years ago, I think, and it has several streams. One on software engineering, one in distributed system, one in intelligent system, and then there's other 3 streams that are sort of running in parallel to these streams, and they are somewhat different. There is one on embedded system design, which is run by a separate institute of the faculty called Alari. And then we have the computational science master, which is actually starting, I think, next year, and this is run by a separate institute, again, of the faculty, which is the Institute of Computational Science. And then we have applied informatics, which is a program intended for people that do not have a bachelor degree in computer science, but have a more practical degree in computer science, which is what you get in Switzerland if you attend a university, a technical school as opposed to a university. These masters are 2 years, and they consist in mostly courses. There's a core of courses at the beginning that are common for all these masters, and then for the first semester, and then for another 2 semesters you do courses that are very much related to the topic of your master, and then there is a last semester where you do a project with one of the professors of your choice. The professors also are in charge, let's say, of the PhD program. We have a PhD school, but when you do a PhD, you get attached to one professor and therefore one area of research. And currently we have 18 professors, although we are hiring another 2, and we have very different area of research. There's some material there where you can see the name of the professor and the areas that we work. The area goes from software engineering to graphics to information retrieval to computer to design of VLSI algorithms and all sorts of things, basically. And both the master and the PhD program are sort of recognized all over Europe and so on. And we have scholarship that we give to students to attend the master and also to do a PhD. These scholarship are on a application based, and they will be given to the best applicants that we have. I can give you the details maybe later on the number of the number of grants that we have for master and PhD. Usually PhD students work in the PhD program also into a project which can be funded by the European Commission or the Swiss National Science Foundation and so on. And we have a limited number also of PhD positions that are not attached to any project initially, but that they will assume to be attached to a project maybe later on when together with the professor an area is identified and a project proposal is submitted. So this is a quick introduction. As I said, if you have any questions right now, I'll be happy to answer that. Otherwise, we can go on with the topic of my lecture.
Actually, before we
go ahead. Yeah.
I wanted to ask you a question. Who is here interested in master's program? And who is interested in the PhD program? Okay, thank you very much. So we just know we're deciding about the structure of the exam later today, and we will let
Okay, good. So then I'll start talking about the topic of my little course here, which is distributed information retrieval. This is an area of research where I've been working for several years, and before actually I start talking about this course, I should acknowledge the help of one of my students, which was one of you a couple of years ago. Maybe some of you know him. He's called Ilya Markov. He's now 2 years ago he attended a course. Or was it? No, yeah, 2 years ago. He attended a series of lectures like this, which I didn't give actually, but was interested in information retrieval, applied to be a PhD student in Lugano and was accepted, and now he's working with me exactly on this topic, and together we developed part of this material, which we gave this year at the distributed as a tutorial in distributed information retrieval at the European Summer School. At the European Conference on Information Retrieval in Milton Keynes in UK. And later this year, in September, we are giving an extended version of this little course here at the Russian Summer School in Information Retrieval in Voronezh. Am I pronouncing it well? Okay. As part of the program of the summer school there. So this course here is sort of in the middle. It takes part of the material of the tutorial given at the ECIR. But I had to attach at the beginning a part on information retrieval as the standard information retrieval, since I didn't know if you had the right background. Obviously, at the European Conference on Information Retrieval, we would assume that people knew about information retrieval. So the objective of this course is then to give you an overview of the area of research of distributed information retrieval, highlighting the key elements and the key technological component, showing all methods of distributed information retrieval, try to solve specific problems that are a sub-area of information retrieval, and also showing how this technology can also be used in other areas of research. And I put some references in here, some key references. Obviously, there may be a lot more than what I put there, which should help you if you want to know a little bit more about some of the topics, to find more about this. So this is what this little course will cover. First of all, I'll give you a background in information retrieval. How many of you here know about information retrieval? None. Good. Then that was a good choice to put the background there. So after that first point, you will know a little bit more about information retrieval. Not a lot more, but enough to be able to understand what distributed information retrieval is and the complexity of the distributed information retrieval area. Then we'll talk about different distributed information retrieval architectures. And among these architecture, I'll choose one, which is the broker-based architecture, so broker-based distributed information retrieval, which is the one I will go deeper into. The other architecture, I will not be dealt with because of time. And so that will be by far the core of this course. More than a third of the course will be on this topic. Then we'll talk about the important issue of evaluation, how evaluation is carried out, what kind of collection and we have, and then we'll talk about application of the IR to other areas. Right. Okay. So let's get started with the background. Okay. So as I said, since distributed information retrieval is a sub-area of information retrieval, you need to know about what is information retrieval, what are the objectives of information retrieval, and what are the underlying technologies that are involved in the information retrieval. Because distributed information retrieval is just a sub-area that does a very specific task in the context of information retrieval. So the objective of this part of the course then for me is to give you a brief overview to the main concepts of IR. Right, okay. And the concepts that we'll be looking at are what is information retrieval, what's the difference between information retrieval and other areas of, and other information systems, let's say. And then we'll talk about the main components of information retrieval, in particular the two components of indexing and querying. Because of the importance of the topic, we'll also talk about two other important elements, which is the IR models, that are the underlying models, let's say, for retrieving information, and then we'll talk about evaluation. So, okay, I'm assuming that all of you use search engines. So, if you use a search engine, then you're using an information retrieval system. A search engine like Google, Yahoo, and so on is just one example of an information retrieval system. Because information retrieval system is basically, well, the technology behind an information, a search engine, it's information retrieval. Okay. So, but it's not. But search engines are just one simple example of the use of this technology. Well, maybe not so simple, but one example. To define information retrieval is also quite difficult because it touches, as we will see, it touches a lot of different applications, a lot of different areas, and a lot of different tasks. So. I'm here reporting perhaps one of the oldest definitions, which is that information retrieval is concerned with structuring, analyzing, organizing, storing, searching, and retrieving information. Now, this is also a little bit generic as well, because here we talk about information. One could say, well, you know, isn't a database management system doing the same? Isn't it, I don't know, a file system doing the same? Okay. No, and that's what I will try to make you understand in the next couple of slides. So, first of all, also I want to delimit the area of information retrieval. Here we will talk about textual information retrieval, where I mean that we are dealing with textual document only, because another important area that is part of information retrieval is multimedia information retrieval, where you are actually not retrieving textual document, but you are retrieving video, you're retrieving images, you're retrieving audio, you are retrieving all sorts of different things. Okay, here we'll concentrate on text and on textual document. Well, but for example, web pages are textual documents. Okay. And despite the fact that they contain multimedia, the multimedia part is not actually indexed as multimedia, but is indexed as text. So you can understand that textual information retrieval is by far the area that is used the most. Right. So what do we mean for a textual document? Well, for a textual document, we mean anything that can carry some semantic information, some semantic content that has this content in there, which is the interpretation that you give to the text, but also that may have some structure as well in which the text is organized. As I said, a typical example is a web page where you have, you know, the title, where you have some fields that get rendered in different way. But another example could be I don't know, a patent, or a newswire, or a scientific article, or anything like that. You know, and as you can see, they are really quite different. You know, if you look at a newswire, for example, the language is totally, it's very short, it's going to the point, it's very, very compact, just to get you some information. There's no opinion. There's no. They're not trying to make a point. If you compare that, for example, with a post in a blog, that's totally the other way around. You don't have, or you have very little facts. You have mostly opinions. And, you know, depending on the person that reads one or the other, can also make his own mind of what these things mean. That's why information retrieval is so difficult, and it's so different from, for example, database management system, where the information that gets stored in a database record is usually structured information that is supposed to report a fact. I don't know, for example, my name, my surname, my age, my address, and so on. So it has a very well-defined semantics. It has a very well-defined structure. If you want to put my age, you expect there to be a number, okay? And you will interpret the number in a particular way because of the field being age. If you compare that with a piece of text, for example, the description of the faculty, there's numbers in there. There's names. There's dates. How do you distinguish, for example, a date from the number of students that we have? Okay, so that's the complexity and the semantics there. So the core issue of information retrieval is comparing. Is to be able to retrieve this textual document in response to a query. So we assume that there is a user that has an information need, who wants to find some information that contain facts or opinions or anything that is relevant to his own information need, and issues a query. And we want to determine the document that is the best match to this query. So the document that will contain that information. This is totally, and so notice that here I talk a good match. While in database record you will assume an exact match. If you want to find out the age of Fabio Crestani, you issue a query in SQL or something like this, and you are expecting, because you're saying I want the age, you expect there to be a number, so you know what you expect, so you know exactly the semantic and the structure of what you're getting. And if your query contains my name, if you misspell my name, you will not find my age. Okay, because the database management system will try to make an exact match on the content of your query with one of the records in the database. In this case, maybe using the name. Sorry. So in information retrieval, for information retrieval, this is not sufficient. Okay, if I want to find information about the faculty of informatics at the University of Lugano, if I misspell informatics, by the way, you will find the faculty of informatics at USI. Okay, so one could say, well, where's the University of Lugano there? Well, that's because being the faculty, the University of Lugano in the Italian part of Switzerland, the legal name of the university is Università della Svizzera Italiana. Okay? Now, I want to be able to find information about this, even if I write University of Lugano. And a good information retrieval system will find that. We'll find that if you misspell informatics. We'll find that if there are, probably 20 Luganos around the world, and should be able to do that for you. And this is all. So he has to be able to deal with the complexity of the natural language. So also, one of the things about information retrieval is that in information retrieval we have many different tasks. These are all related to the fact that we have different documents, that we have different users, and users wanting documents for different reasons. So when we talk about search engine, for example, we refer only to one specific task of information retrieval, which is what is called ad hoc search. Ad hoc search is concerned with finding relevant documents, finding documents that are relevant to an arbitrary text query. So a user submits this information needs, write down a query that is supposed to represent that information need, and wants to find documents in response. The system returns this document, the user looks at this document, if he finds one that contains the information, fine, otherwise they issue another query. But the process goes like that until the user finds the document, and then his happy goes away. Okay? When he comes back, that will be a new session. Okay? He may issue the same query, but for totally different reasons. So the system will assume that this is a totally different interaction. That's totally different, for example, for filtering, which is another area of information retrieval that we will not talk here, which is instead concerned with finding documents through a stream that are relevant to a user profile, in this case, so to a user long-standing interest. For example, I want to be able to record all the conversation that talk about my name, okay, or the name of a company that I work. Yeah. That's, by the way, this is amazing, but this is done in the world. It's called media monitoring. There are companies that do this, and they just monitor, maybe all the channels in English in the world, the streams, and they record every single piece that mentions the name of a company, a particular company, for example. In that case, you have to identify a relevant new document to a user profile when just the document goes through this stream. Okay. Then we have other tasks like classification, which I'm sure you know what it is. So identify a relevant label for documents. So saying this document is about sport or this document is about politics. And question answering, which is giving a specific answer to a question as opposed to find a document that will contain the information. By the way, feel free to ask questions anytime. Okay? Yeah, go ahead.
What is the relation between IR and what we know as knowledge extraction, which is used in...
Okay. You mean knowledge extraction or information extraction?
Knowledge extraction.
Okay.
To build a database.
Okay. All right. Okay. Some people call that information extraction, so it's basically the same thing. Okay. Well, information extraction systems are part of an area which used to be part of information retrieval as well, which is text mining. So basically what you do there is that you use, for example, imagine you want to mine all the web pages that contain prices of hotels in St. Petersburg, okay, and populate a database on that. So what do you need first? The first thing you need is to identify pages that contain information about hotels, okay, and that's the information retrieval part. Once you have identified that, you pass this set of documents to an information extractor system, or that could be some text mining system or whatever it is, that will process each and every page to extract this information using some shallow NLP, natural language processing technique. So the relation is this. Usually an information retrieval system is the first component of an information extraction system to identify the pages that are relevant, and then some other process extract the information and populate the database.
Okay, so what is the question answering then?
Question answering it's a further step. So it's a system that is composed of the three things. So it will first find, let's say I want to find out what is the depth of the Nava? Is that Nava, the river here? Yeah. Okay. So I can put this into an information retrieval system or a search engine, which first has to find out pages that talk about the Nava River, and the particular Nava River that go, from St. Petersburg, I suppose, and then it will have to extract sentences that talk about the depth of the river, and then make up an answer saying the depth of the Nava River is, and the number. Okay. It's totally natural language processing, but yeah, texting. Yeah. So it's slightly different than information extraction, because in information extraction you have a form that you want to fill, basically, which is your database record. Here you don't have a form initially that you want to fill, but you use similar technology. Yeah.
And there is no inference of right answer?
No. It's mostly text processing. Yeah. So the page need to contain the number, which is the depth of the river. Otherwise, there's no way that you can make it up. Yeah. So in fact, if you want, the area of information retrieval, as I already explained, is different from databases, but it's also different from knowledge-based system, which do some inference. There's no inference being done at all in information retrieval. And also for the rest of this course, we'll concentrate on a doc search. So a user issuing a query and wanting some documents back. What does he want? Why does he want the documents back? Well, he wants the document back that are relevant to his query. And that, in fact, is the biggest issue in information retrieval, the concept of relevance. There's been, a lot of, let me say this, in information retrieval there's two groups of people. There's the computer scientists and the information scientists that work on this. The computer scientists are more concerned with saying, okay, I don't really care, about the concept of relevance. I'm caring about building the best system, that has to be fast, has to process millions of documents at a minute, has to, find the document that the user likes. And then there is the information scientist, which are more concerned with, this user, how do we go about helping this user formulate a query? What does he mean when he says that? How should we go about, modifying the original query of the user to incorporate, for example, the background of the user, incorporate the intention of the user or the task that he's doing. So this is why the relevance is basically perhaps the biggest issue in information retrieval, because a simplistic definition of relevant is that if a document is relevant, if it contains information that a person was looking for when it submitted a query, but this, I'm sure that each one of us can issue the same query and probably have totally different idea of the relevant document, because we have different background knowledge. We may be doing this querying in the context of a different task. You may be wanting this information just out of curiosity, or you may be writing an essay about this. You may want to tell to somebody, so there's different context. Also, think of a simple fact. Once you see a page, and that page may contain all the information that is relevant to you. You see it, you think it's relevant. You see it the second time, it's not relevant anymore. You know there's information. You don't want that page anymore. Okay? That is one reason why, for example, they have to eliminate duplicates in web search engines. You don't want to see 10 copies of the same page in your ranked list. One is enough. The second one, it will probably be relevant as the first. But once you see the first, it's no more relevant. Okay? So, then style as well. If you want information about a particular topic, you may want a long document, you may want a short document, you may want something a table that reports some facts or the opinion about something. Okay, for an hotel, you may be interested in the price, you may be interested in the opinion of somebody that stay there, you may be interested in the location, you may be interested in a lot of things, which actually will come back later when we talk about vertical search. So an IR system can only estimate the relevance of a document using some complex mathematical model that is supposed to reflect the interpretation that we give to relevance. And that's why also we have so many models, while if you think, for example, in databases now, there's one dominant model, all the rest sort of disappear. Right, and also this makes it clear why it is important to evaluate in information retrieval. Okay, you may have, if I ask you, is Google better than Yahoo? Well, you don't have a straight answer. Okay, if I compare instead two database management system, you can say, well, is I don't know, Oracle better than some other system? Then you could say, okay, well, let's run it on 1 million queries, or let's see if we can, index, 2 million documents in less than a minute. Okay, well, the one that wins is the West. Okay, in IR it's totally different. Okay, as the search engine example shows. Okay, so what is the IR process and what are the IR components? You can read it. Quickly, because I'm sure, if you think of the way you use a search engine, you will recognize yourself there. So this is you, okay? You have an information need. You want to find something, okay? Well, then you say, oh, should I write down this query? And you write it down. Probably if the day after, you probably may be writing it differently. But that day you wrote that query, okay? Well, your query gets submitted to the system. So what is happening between these two lines here is what is happening inside the system. Your query gets processed, okay? Something happened to your query. We'll talk about that later. The query, and a query representation is produced. What has happened already beforehand is that the system has acquired somehow documents, has processed the documents, and have stored. This is outside the online phase of the information. Well, it's outside the system, basically. This is simply stored information. What happens is that once he has stored all this information about the document, then he has to compare your query representation with the document representation that you have for every single document. Some matching process goes on, and this process is modeled by an information retrieval model, and some documents are returned. This could be a set of documents or a ranked list. The ranked list is the dominant now paradigm. So you see a ranked list. And this ranked list could be a total ranking of the entire collection of the document. But being that this collection is huge, you're not going to see it all. So, the first 10, the first 50, the first 100, that's what you probably look at. If the collection contains billions of documents, you don't care. You just want to look at the first 10. And in actual fact, search engines show that you want to look probably less than 10 as well. You found the document that contained the information. This is your assessment. Fine. Otherwise, you issue a new query. Maybe you modify your original one, and you go through this process again until you're happy with what you found, and that's it. So you leave. The next time you come, the system will assume that you are a totally different person, that there's no history. Well, there may be some history, but the history is not used basically to help you go through your next query. Right. Okay. So there's two important processes here: the indexing and the retrieval. Okay. The indexing is basically the process that produces the representation of the documents and the representation of the queries, and the retrieval or matching or processing of the query, it's the way of match the document and the query representation to produce a ranked list of documents or document ID to show you. Okay, so let's go through the indexing first quickly. Okay, what is the indexing process supposed to do? Well, first of all, here we assume that the documents, we already have them. Okay, in many cases this is true. In digital libraries and for example, your desktop search, the documents are already there in your disk. But in some cases it's not. So the search engine, for example, does not have the document, has to gather them. So the first part would be the text acquisition phase. There would be a crawler or something that goes around fetching the documents. Then there is a text transformation where the documents get transformed into index term, so in some representation. And then this representation that every document has been going through will be optimized through the creation of some indexing structure that will make it very fast then when you want to find a particular document that has a particular term. Okay? So the text acquisition, as I said, may involve crawling. This could be crawling the web, crawling a network, or for example in enterprise search, or crawling simply your disk if we are talking about desktop search. By the way, these are all different phases of information retrieval as well. It's just the collection that is different. Or it could be just monitoring a feed. Okay, this is particularly done in information filtering, but sometimes it's done also by some information retrieval system, like for example web search engine that monitors news feeds, blog feeds, video feeds, and so on. These documents then are stored in a document data store, because then sometime when you want to show to the user quickly the document, you don't have to fetch it from this original source, but you can just take it out from your document data store. So in the case of the web, this document data store should be as big enough to store the entire web. The second phase then, once you get the document, and then we take one single document, we want to process that document so that we can extract information from it. Now, because of the documents being text and because text having many different interpretations, the way this process of text transformation, this process of indexing, is a very complex process, and I have no way here basically to go through all the different phases and explain the way they are carried out. But it usually involves a number of steps, where the first step, for example, it's a parsing process where we take this text and we break it up in tokens. Also attaching perhaps the position that the token has in the documents. For example, in the particular structural element of the document, or maybe in the stream of text in the document. This is very useful if you want to find, for example, names that are made up of two words, like Fabio Crestani, as opposed to find Fabio at the beginning of the document and Crestani at the end, and this being totally about different topic. Okay, so. Then we have a phase called stopping, where we remove words that have no semantic meaning. We have another phase called stemming, where we take words and we process them in such a way that we eliminate lexical variants of the words. For example, to have not to have problem with plural and singular or different verb tenses and so on. So we reduce words to a common stem. Then we sometimes we do a link analysis on the document if there are links going into the document or links going out to the document, because some of these words that we are processing may be actually anchors of links, and this is done obviously in web searching. Then we can do some information extraction, for example, to extract specific words that identify name entities in documents, because that need to be treated, as a single element rather than the two elements, like St. Petersburg, the two words that make up St. Petersburg, or the University of Lugano, which we want to treat it as a word, as opposed to university, maybe having a document that says, in Lugano there is a university, as opposed to finding a document that talks about University of Lugano. And then we have classification as well. This is useful for identifying if some documents need to be treated in a particular way because they contain, for example, information that need to be processed, for example, for multimedia content or things like that. Okay, so once we've done all these steps, basically what we get is what is called a bag of words. Okay, so a document, imagine this page is a document. We start parsing it, so we are starting, breaking it up in words. And don't think that this is very easy. It's probably easy in English and Russian, because we have space that delimit words. Think of Chinese or Arabic or ancient Egyptian. How do you make up a word from? That's a big part. Then we throw away some words, like for example, to, with, no, and, of. These have no semantic meaning. We reduce everything to small letters. We remove the endings of the plural, for example, and so on. We recognize, for example, the link analysis as one word. The information extraction should be treated as one word, and so on. And we have a bag of words. Okay, we lose the entire structure, and then we don't care about the rest anymore. Right. Once we have this, then what we can do is then we can say, all right, look at this. Here we have words occur a lot of time. Words. Well, only two. Terms. We have pages. So we have words that occur more than once. Okay. Is that important? Yes. If occur more than once, probably means that page, is more about that word than a word that occur, for example, only once. But we may have words that, for example, if you look at all the slides here, you will find that the word term occurs quite a lot, or index will occur quite a lot, or documents probably will occur in almost every slide. So maybe the fact that this page has 2 times the word document is not that important if the word documents occur basically everywhere. So basically we are calculating some document statistics on the words occurrences that we use then to give a weight to these words. Okay, so that some words will be given basically a higher weight because they are good in representing the content of that document. I'm not going to cover the formulas that that you're going to be using to do this. There are different complex formula, and the references are there, but if you want to ask questions, also feel free. Then what we do is that we do a process called inversion. Okay. Normally, if you think you have one document, imagine this is a document, and here we have all the words that occur in that document. When you actually are submitting a query, you are submitting some keywords. Okay. And you want to find the documents that contain that keywords. So what we have to do, if you think that this is a matrix, where we have, actually, let's say this is term 1, term n, and this is document 1, document k, and here we put, at a particular position here, we put the weight of the term ij, the term I in the document j. Then we want to invert this matrix so that instead of having that a document is represented by the words, we have the words. Each word there is represented by the document in which it is contained. Okay? This will help us then to, once we build some indexes, to find out the documents that contain that word and being able to retrieve them, and by combining and ranking them by combining the weights with which that terms occur in each one of these documents. And because often these indexes will be huge, think of all the possible words. Actually, this is being distributed actually, but think of all the possible words that occur in the web. Okay, in any language, plus spelling mistakes, plus names, and so on. You have a huge list, and there's no way that you can store that in main memory. There's no even way that you can store that in a single file system. You may as well break it up, distribute it, and put it across different file systems. This is actually part of this area is what Fernando Pedone was working that I think gave a talk here last weekend. In this case, with these distributed indexes, then get processed once you get submitted a query to produce a unique ranking of the documents. Okay, and this is what is happening when the query processing is being carried out. The query process is composed of three main components: the user interaction, the ranking, and the evaluation, where the user interaction involves providing the system with an interface that will parse the query. The query may be a very simple set of keywords which need to be processed the same way that we process the documents, so removing plural, removing words that have no meaning, recognizing words that need to stick together, like University of Lugano, and so on. But also may involve, more complex query languages where, you want to give more, you want to say this term need to be present and something like that. Also, sometimes you may want to expand this query if the user wishes so. For example, with additional words that are synonyms with the words that are already present. And this user interaction also involves presenting then the results to the user, and so constructing, for example, this rank list and maybe representing each document in the rank list by a surrogate of the document. Think, for example, at the results that you get from a web search, and you have the title of the document, you have the URL, then you have a small summary of the document there. So basically, these are called document surrogates. And again, information retrieval is what helps doing surrogates. Okay, so the ranking, obviously, once a query is submitted, using those indexes will produce a ranking. The ranking is presented to the user. Sometimes there's some performance optimization is carried out. So, for example, we may discard duplicates that we get in the stream, in the rank list, and and if the indexes are distributed, this query processing also need to be distributed across the environment. This, in fact, the distributed query processing is what originally started the field of distributed information retrieval, which at the beginning wasn't really distributed information retrieval the way I will explain you here, but it simply was information retrieval on a distributed system. Okay, where you issue the query, and simply because the indexes were held by different server, the same query was going to each one of the server, which would process the query and give a list of the documents back, and then a merging will be carried out. But this is relatively simple because there is the same retrieval model. The indexes the system will build the indexes in that way and put them the way they are. So this is what is called a total cooperative environment. It's one single environment, and so it's very easy then to build this list. This is totally different with what instead distributed information retrieval is now, and which will be what we will talk later. And finally, when this is normally not seen by the user, but you should be aware that search engine basically log every single user interaction that you do with your through the Google, the Yahoo interface. So they will log your query, they will log the time and the machine number from which the query is coming from. They will look at the interaction that you go through the system. They will look, for example, at which of the result you will click in the rank list, and they will do what is called a ranking analysis. So they will use this information, for example, to tune their ranking system. So I'll just give you a quick example. You can even it's difficult to verify, but you could verify if you want. If you issue a query, if let's say a bunch of users issue the same query and they never click at the first document, they always click at the second, you can be sure that in a matter of maybe hours, the second document will become the first. Okay, because if everybody thinks that the second document is the one that should be at the top, through some ranking analysis that gets done also automatically by search engine, the ranking will be adjusted. And also there will be also some performance analysis on tuning the efficiency of the system and so on. Okay, so a topic that is important in information retrieval, but again, one of the I don't have time to go deep into this because this could be this single topic could cover more than double the time that I have here for the entire course, is retrieval models. So the retrieval model is a mathematical model that define the search process. Basically, they define the concept of relevance and how we match the representation that we have of the query with the representation that we have of the documents. And we already seen that the documents most of the time are just bag of words, but even if they are bag of words, there's many different ways that you can compare two bag of words. Okay, and so a lot of models have been proposed. Here is some classification. There are many around, but you can find it on Wikipedia, so it has this advantage. These are all classes of retrieval models. Okay, each one of these little boxes contain several versions of models as well. And they can be classified as set theoretic. For example, think of the Boolean model. Okay, what do you do in a Boolean model? Well, you issue a query with some Boolean operator, and you want to find a set of documents that matches that Boolean expression. Okay, but there's standard Boolean. There's extended Boolean as well with the proximity operators and and other things like that. Then there is an algebraic set of models. For example, the vector space model, which assumes that these bag of words represent vector in a space, and you want to measure if a document is relevant to a query by the similarity of these vectors, which could be, for example, cosine correlation or some other similarity in a multidimensional space. You have probabilistic model, for example, where you're actually trying to determine if a document, the probability of observing relevance, given that you're observing a document and that you have being issued a query. Okay. Now, these three actually correspond to three big definition as well of relevance, which is a perfect match. In a Boolean, think of a Boolean, way of carrying out a query. Partial match, where you have, for example, the vector representing the query and the vector representing the document, sort of getting some form of similarity, and the best match, in a probabilistic way, where you maybe have a cost function as well associated to finding a document or not. And again, this is in a very simple way of doing this, you assume that there is no interdependence between terms. This bag of words is made of terms that are one independent from the other. But we know that this is an assumption that is not true in reality. Okay, if I find in my document the word tank, okay, and then I have and then I have other two words. Okay, the word army and the word butterfly. Okay. Now, if I ask you, would you bet, would you bet more money on the fact that there will be the word, given that you found the word tank, that the word army will occur there, or that the word butterfly will occur there? Well, I'm sure where you would put your money. Okay. So that means that there is some interdependencies. They are not independent. Okay. So all these models, almost all these models can be extended to consider also term independence. But think, for example, how will you calculate the term independence if you have a collection of even 100,000 documents, which is probably several order of magnitude smaller than some of the collection we use, or a collection like the web. And think of all the terms there. A collection with 100,000 documents will probably have 4 or 5 million terms. Think of how you're going to calculate the mutual interdependence of 5 million by 5 million terms. Okay, a matrix like that. Okay, and what information you're going to need to be able to do that, because this matrix will be very sparse anyway. You will have no information. You will have no documents in which the word butterfly and the word Viking occurs, for example. Okay, so can you estimate if there's any dependence between these two words? And the fact that you cannot find the document where they occur doesn't mean that there's not. Okay, it simply means that your data are not enough. So anyway, there are ways of doing this. I don't know if you guys heard about latent semantic indexing, or if you heard about spreading activation neural networks. I'm sure you heard about neural networks, but the use of neural network in information retrieval. And this is when immanent term dependence, where when you want to estimate the term dependence out of the data that you have, or you want to have transcendent term interdependence, where the term interdependence is not going to be extracted from the data that you have, but it's going to be extracted from some higher level semantic components, let's say, of the document. And so here we have another set of documents, another set of models, like fuzzy sets, logical imaging, and things like this. Okay. So again, as I said, this could be the topic of several hours course, because each one of these classes of model, as I said, this is not a model. It's pretty mathematically heavy. For this purpose, suffice to say that an information retrieval has one model. Okay, one model may not be the best one, but that's the one that was chosen for that particular system. The choice of that model probably reflects the fact that they are dealing with particular kind of user, with particular kind of documents, and so on. So, for example, a model that may work very well for news wires may not work at all for patents or blogs. Okay, a model that works very well for finding. By the way, all these documents can also be used not only to find what is called, I forgot here, topical relevance, but also to find, for example, opinionated relevance. Okay, something that is relevant and then express an opinion which is similar to yours. all of this, to finish basically this introduction, brings me to the importance of evaluation. Because we have so many, why do we have so many models? Okay, we have so many models because somebody says, okay, this is what are we doing? We have this kind of users, I don't know, lawyers, this kind of task, well, this kind of documents, patents. What do they want this document for? For example, prior art search. Okay, so being able, the lawyer is supposed to write a document that says, you know, this patent is new because nothing exists before in the patent database that is related to this. Okay, you want a patent, I don't know, well, I can't think of anything, but if you want to patent something, you need to make sure first that nobody has patented before. Okay, and if somebody had patented something similar, you want to say it in your document why your patent is different from that patent. Okay, this is one specific task. Then you may say, all right, you know, I'm going to try with some of this model. This model is the best. Okay, you can be sure that somebody else will come and say, no, I think this model is the best. Okay, and and then you say, prove it. Okay. How do you prove it? You know, well, ask my lawyers. I say, yeah, ask my lawyers. Okay, so what do we do? Well, it means that we need to have a framework where we can do this evaluation, and this framework will say, okay, how are we going to prove this? You know, out of you know, for sure, without having you know, opinions involved. Well, we need to have, for example, a collection of patents. The same. You know, my system is going to use the same collection that you use. This is what is called sometimes corpora. Then, we're going to say, right, we need the same set of queries. Otherwise, you know, for these queries, my system could be good and yours can be bad, but we may have some query that it works the other way around. So let's get a good set of queries, 50, 100, something like this. And then what are we going to do? Well, we need to say, right, we need to have unconfutable opinion that this document is good for this query. Okay? And some metrics that will enable us to evaluate that. Okay? So this is what this information retrieval has been doing for 40 years. Okay? Inventing this collection, finding out this collection, inventing these queries, finding relevance judgment, and proposing evaluation metrics. Collection may go from this is, you know, from a collection like CICM, which was used several years ago in the 70s, which was about 3,000 documents. Okay, with a very short document. The average number of words per document was 64. More recently, we have, for example, 3 years of Associated Press newswires. Okay, that's about 250,000 with, you know, definitely longer documents. But then, for example, another collection that we use, well, we've been using since a few years, is the .gov collection, which is Gov2 in this case, which is the entire dump of the .gov domain on the web. Okay, which, you know, it's 25 million documents, you know, and pretty long document because they are governmental document describing things that has to do with the U.S. government. Okay, these are 3 different collections. You can be sure that what works with one will not work with another one. We have also different kind of queries. For example, for CICM, the queries were pretty long. There were only 64. The queries were pretty long, about 13 words, and there were about 16 on average document relevant for each of these queries. But then, you know, compare that with the .gov, where we have 150 queries. The average query length is 3 words. Okay, why is that? Because that's more similar to the kind of query that people issue on a web search engine, which is 2-point-something words on average, and a lot more relevant documents per query, because again, there may be duplication of content and things like this. Okay, and usually the query that we use contain a title, a description, for example, and the description is supposed to represent the user information need. So, for example, here the user wanted to know how are pets or animals used in therapy for humans and what are the benefits. Okay, and we have a narrative that describes what the relevant document should be about. So, for example, relevant document must include detail on how pet or animal-assisted therapy is or has been used. Relevant detail include information about the therapy program, Okay, so basically, then at this point, it's easy to use whatever information you want from this to write the query, submit it to your system, my system, and my the alternative system, produce 2 ranked lists, and then compare the 2 ranked lists. How do we compare them? Well, the 2 main measures of information retrieval are precision and recall. If you consider A, there's didn't come out very well. There's a line here on top. Okay, so if basically A is the set of relevant documents that the entire collection contains, and B is the set of retrieve document, okay, the one that your system retrieved, then recall is both they have the same numerator here. So it's the document that are retrieved and that are relevant at the same time, okay? The good documents, basically, that you see in your rank list. Then, if you take that denominator and divide it by the number of relevant documents in the collection, you have the recall. That is, how many good documents was I able to retrieve, and the out of the total number of good documents that are there. So the percentage of good documents that I was able to retrieve. The precision instead is the percentage of good documents that are in my rank list. Okay, so to give you, well, this is an example of how you produce the ranking, but we can skip that. Imagine you get the top 10 documents in your web search. Okay, if let's say 7 of them are relevant, your precision will be 7 over 10. Okay, 7 good documents out of the 10 that you're seeing. Your recall, assume that the web contains 1,000 documents that are relevant, it would be 7 over 1,000. Okay, which brings me also to the other fact that there are tasks for which precision is important and tasks for which recall is important. In the web, if you actually see even one document, you don't care if there's another 1,000 on the web that are relevant. You've seen one, you got your information, and you're happy. Okay? So you don't care about recall, you care about precision. You care about finding that document at least in the top 10 that you're getting back. But in the previous example, where I was talking about this lawyers that was looking at search for patent for prior art, he is interested in recall. He cannot afford to miss one document that is exactly the same patent that his client is going to propose, which maybe it's in position 10,000 in the ranking. He has to go down to 10,000 to find that document. Because if he doesn't find it, then he files it. He files the patent. And the patent often says, oh, yeah, but there was already another one. Well, the patent is rejected, and all the money of the client and all the time of the lawyer is lost. Okay? Right. Okay. These are by far the 2 most important measures. There's others, mean average precision, discounted cumulative gain, and so on. Also, some measure that combines these 2, recall and precision, like, for example, the F measure, which is the harmonic mean of precision and recall, so that you basically can combine and give them in one single value, for example, more important to recall and less to precision, and so on. And again, here's some set of references to find information about basic information retrieval. This is a very old reference. It's also available as a PDF online, but it's still very valuable. This is a very new book that came out, and this is something in between the proceeding of a summer school where some of these issues were discussed. Okay, any questions on this part? No?
Could you explain once more on page 26 what was for A and B?
Yeah. Okay. I think here there's a little problem that there is a. Okay, let me actually do it on the slide, on the blackboard. So A, to refer exactly to that, is the set of retrieve documents. Okay. Let me see. Oh yeah, relevant. Yeah, you're right. Okay, this is no good. I'm getting there. Maybe I should write one letter with one color and better. Okay, so A is relevant, B is retrieved document. Running out. Sorry?
It's the best place of the board, maybe.
Oh, okay. I'll write here now. So if we do A intersection B, okay, this is the number of documents that were retrieved and relevant at the same time. Okay? So if we divide this by the number of relevant document, we have the proportion of the documents that are retrieved and are good over the ones that are good in my entire collection. Okay? And this is what is called a recall. Okay? So how many documents in my that are relevant inside my collections were actually retrieved. Okay? The proportion. If we take the same, okay, so how many relevant documents were also retrieved over the number of retrieved documents, I have the precision. Okay, is that clear now? Okay. So let's take this example for it. Okay. Yeah. Okay, these are relevant documents. The black ones are relevant documents. The white are not relevant. Okay. Here we have two systems. The system 1 produced this ranking. System 2 produced this ranking. Okay. Now, notice system 1 produced the first document is relevant. Okay. The second is not relevant. No. Okay. Okay. So at the first document, after having seen one document, what is the precision? Okay. The precision is 1. It's 1 relevant and retrieved documents over 1 document that's been retrieved. Okay. What is the recall? Well, I've been seeing 1 relevant document over 6. Okay, 1 over 6. Then at the second document, the recall is still, I've seen only 1 relevant document, so it's still 1 over 6. The precision, though, decreases because I'm seeing 2 documents and only 1 is relevant. Okay, so it's 1 over 2, 0.5. At the third document, I am retrieving 2 documents out of the 6 that are relevant. Okay, so it's 2 over 6. Okay, the precision, it's 2 over 3. Okay, and so on. So as you can see, recall increases until I found the last relevant document in my collection. Precision goes sort of up and down. Okay, and so if I ask you which one of these two systems is best, which one would you say? Which one would you prefer? Yeah.
Well, as you said, for web, when interested in precision, so that...
Sorry, one at a time, sorry?
For web, when interested in precision, so the first is better. But in general, precision, no, I believe.
Well, if we compare them, up to this level, okay, they are the same, okay? So, really I need to, obviously, so if I go down to here, they are the same, okay? But if I say, if I'm going to look only at the first 3 documents, okay, which one would be best? First one, yeah, because in the... Exactly. So, this one is probably, I would say, so it's clear that if this is the same query, okay, and these are 2 systems, the only difference can be they're using a different retrieval model, okay? So in that case, I would say this retrieval model is better for a precision-oriented search, okay? Because it puts the relevant document at the beginning, like I want, for example, on the web. The second system, well, I mean, if we stop there, basically they're the same. But the second system, well, it's less good. Simply like that. Okay. Now, if, for example, for some reason this first the ranking here would have been a lot longer. We would have more relevant documents, and for example, and this system will lose some of them. Then I would say maybe the second ranking is better. The second system is better for recall-oriented search. A recall-oriented search that you may think, because you guys are probably used more to search engines, you don't think that there are many recall-oriented search, but there's actually quite a lot. For example, medical doctor looking for drugs, for example, on archives. You cannot say, if you issue a query on the web and you don't find the relevant document in the first hand and you just go away, you don't care. But if you are a medical doctor and you want to find, if I give this drug to this patient who has this condition, will he die or not? Can you say, oh, I only look at the first hand documents, the document that talk about, this condition was in the number 20, sorry, You cannot say that, okay? So you have to go pretty down the list. So your system has to be recall-oriented in that case. He has to find all documents that may mention even slightly that fact. Okay? More questions? No? Do you want to take a short break? Okay, let's take a 5 minutes break.